Now next comes the condition for existence of conjugate lines. Now when do we say the two lines are conjugate is the biggest question of the topic. So let's see the condition for existence of conjugate lines. Suppose I take the two lines L1x plus M1y plus N1 and L2x plus M2y plus N2 are the two lines, then these two lines are said to be conjugate lines with respect to the circle S equal to 0 if I have the condition R squared times L1 L2 plus M1 M2 is equal to L1G plus M1F minus N1 L2G plus M2F minus N2. Where I have R as root of G squared plus F squared minus C, which is radius of circle. So the condition here is that for two lines to be conjugate with respect to the circle S equal to 0, R squared into this must be equal to this times this, where L1, M1 and N1 and L2, M2, N2 are extracted, and R, which is given by the formula root of G squared plus F squared minus C, is the radius of circle which we find using G, F and C extracted from the general equation of circle. The condition for existence of two lines to be conjugate is this. The next is about inverse points. When do we say that the 2 points are inverse points is the biggest question. That is, if suppose I have the circle S equal to 0, then P and Q are said to be inverse points for the circle S equal to 0 if my first condition is that C, P, Q are collinear, and my second condition is that P and Q are on the same side of C where C is center of circle, and the third condition is that CP dot CQ is R squared, that is CP times of CQ is R squared, where R is radius of circle. So let's take the diagram and see how we can understand the inverse points. Say for example, I have a circle S equals 0 and I have the center of circle out here. Now if suppose I have 2 points P and Q such that they are collinear, that is I have P here, Q here and my point P here, then in this case the radius of the circle is R. Then if P and Q are on the same side of C, then CP dot CQ equal to R squared is the condition which makes us define the inverse points. So under these three conditions, we say that the points P and Q are inverse points with respect to the circle S equal to 0 if C, P, Q are collinear, P and Q are on the same side of C center, and CP dot CQ is R squared. Is how we define the inverse points with respect to the circle S equal to 0. Now let's see the inverse points for standard form of circle. That is, if I take the circle in the standard form as x squared plus y square equal to r square, then PQ are said to be inverse points for this if and only if Q is the point of intersection, if Q is the point of intersection of polar of P and CP. So the point of intersection of CP and the polar of P will give us the 2 points to be inverse points for the standard form of circle. So let's see with the diagram. Suppose I have a circle x square plus y square equals r square. Now for this standard circle, the center being origin, I take the center C and I take the point P somewhere here. Then if I say that the polar of P lies here, and then the say CP intersects here, then this is the polar of P and this is the line joining CP, and then the point of intersection of CP and polar of P, if this is Q, then we say these 2 points are inverse points. So under the case, this point Q becomes an inverse point with P, is how we understand the concept. PQ are inverse points if and only if Q is the point of intersection of polar of P and CP, is how we understand the inverse points connected with standard form of circle. Now say, for example, I have a circle S equal to 0 in its general form. Now let me take a point, let me take the center of the circle to be C. Now I have a point P out here whose inverse point I would like to find. So what would be the inverse point of P with respect to the circle S equal to 0? So here let me draw the polar of P somewhere passing through here. So this is polar of P. Now here the inverse point of P is the point which is the foot of perpendicular from center to the polar of P. That is, if this is the polar of P and this is the center of circle, then inverse point of P is the foot of perpendicular, which is Q. So Q is the inverse point of P. So when I just extend out here, I get this to be collinear, as I can clearly see that C, P and Q are collinear, and in this case Q is, which is the foot of perpendicular from center of circle C to polar of P, is nothing but is the inverse point of P. So we understand Q, which is the foot of perpendicular from center of circle to the polar of P, is nothing but the inverse point of P, or inverse point of Q as P, vice versa, is how we understand the inverse point connected with foot of perpendicular of from the polar. Now let's see one of the example problem through which we understand the concept of finding the inverse point through a better procedure. So if I have a problem which says find the inverse point of minus 2, 3 with respect to the circle x square plus y square minus 4x minus 6y plus 9 equal to 0 is the question out here. So here I clearly have the circle S equals x square plus y square minus 4x minus 6y plus 9 equal to 0. And one of the inverse point is given to be, say I take as P, which is minus t minus 2, 3. Now the question is to find the other inverse point. So for this, let me take the diagram. Now here, the center of C, which is center of S, which is denoted by C, is given by minus G minus F, that is 2, 3, as derived from here. Now if I take a circle whose center is 2, 3, and I have a point P which is minus 2, 3, then we know that the polar of P is somewhere passing here, and I have this out here. So we know that Q is the foot of perpendicular from C, which is exactly out here. So Q is the point of intersection of polar of P and CP. If CP is the line, if this is the polar, then polar and the line CP intersect at Q, which gives us the inverse point. So it is essential that we find the polar of P and we find the equation of CP and solve them through elimination method to get the point of intersection Q. So let's see how we can find each of them. So initially, polar of P minus 2, 3 with respect to the circle S equal to 0 is S1 equal to 0 using the formula. So S1 equal to 0 implies x1 plus y1, half of this, which is minus 2 of x plus x1, half of this minus 3 y plus y1 plus 9 equal to 0 is what we get. Now simplifying this more further, we get this to be minus 2x, which is minus 4x, and 3y minus 3y, which get cancelled to give 0, and 4 minus 9 plus 9 gives me plus 4 equal to 0, that is x equals 1. Now this is the equation of the polar P. This is the line x equal to 1. So equation of line polar is x equal to 1. So is what we get. Now next, it is important that I find equation of CP. So equation of polar P is x equal to 1, which I take as equation 1. Now next is equation of CP. So this is polar of P, which is minus 2, 3. Next, to find equation of CP, I consider C, which is 2, 3, and P, which is minus 2, 3. Therefore, if I take this as x1, y1, and this as x2, y2, then I have y minus y1 is equal to, using the 2-point form of line, is y2 minus y1 by x2 minus x1 of x minus x1. So this on simplification gives y minus 3 equals 0 times x minus 2. That implies y equal to 3. Therefore, y equal to 3 is equation 2, which I obtained from finding the equation of line CP using the 2-point form, using the formula y minus y1 equals y2 minus y1 by x2 minus x1 times x minus x1. Substituting each of them, I get this to be this. Now solving these two equations, I get, therefore, Q is equal to 1, 3, which is the point of intersection of 1 and 2. So the point of intersection of 1 and 2 is nothing but 1, 3, which I have obtained, and this is nothing but the inverse point. Also, that implies Q equal to 1, 3 is the inverse point of P with respect to the circle S equals 0, is how we understand the finding of the inverse point of the circle with respect to the other point. So, finding of inverse points requires solving of two equations to find the point of intersection of two lines by elimination method. Now let's see how the equation of chord can be connected with the middle point, and hence finding the equation of the chord through its middle point, the given midpoint. So for example, I have a circle S equals 0, and I have the center of circle here, and I have a chord AB, or I have a secant through which I get the chord for the circle in this way. It intersects the circle at AB, and let me say this is the midpoint of the chord AB, and let the coordinates of the midpoint be x1, y1. So if M is the midpoint, is the midpoint of chord AB, that implies equation of secant AB or the chord AB or chord AB with respect to the middle point is S1 equals S11, is how we understand the concept of middle point connected with finding equation of chord. So equation of chord or the secant with respect to the midpoint x1, y1 is S1 equals S11, is how we understand the equation of chord through the middle point. Now that we have discussed about circles and the position of points and position of lines with respect to the circle, now let's come to the understanding of what happens if two circles have their relative positions changed. That is, if the two circles touch, or if the two circles intersect, or if the two circles are disjoint. So let's come with three cases and see identically on what are the different properties studied under these three cases. So initially, to come with case 1, case 2 and case 3, where the first case is intersecting circles, touching circles, and disjoint circles are the three cases which we have here. Now, as I see the intersecting circles, I see that the two circles are said to be intersecting if they are in this form. They are intersecting circles because they have some overlapping region in between. Therefore, these two are intersecting circles. Now, when I say touching circles, I have the two circles touching each other, is how we understand. Or the possibility is that this can also touch inside, where this is called touching externally, and this is called touching internally. Because the two circles are touching inside each other, and here they're touching outside. So touching externally and touching internally. And disjoint circles are the circles which do not intersect. There is no overlapping region like here. They're just way apart. There's some space in between the two circles. So with these three cases, we study the different types of properties involved with this. Now, as I come with the relative positions of circles, now I connect with the tangents connected with these three types of circles. So let's see the tangents connected with the relative positions of circles with each of three cases. Now let's connect the relative positions of circles with the number of tangents which can be drawn for that position of circles. Now, as we have taken three different cases of circles which are possible when you take them in relative positions of combined circles, now let's see how the common tangents can be drawn. Now we know that a common tangent is a tangent which is a tangent to both the circles together. Suppose I have two circles which are like this, then this is a common tangent because this line is a tangent to the circle 1, and this line is also a tangent to the circle 2. So if a line is a tangent to both the circles at once or at the same time, that tangent is called a common tangent for both the circles. Now, as I see for these two circles being intersecting circles in case 1, if I draw a tangent here, and if I can possibly draw another tangent out here. So two tangents can be drawn, common tangents can be drawn for intersecting circles. Therefore, for intersecting circles, I can draw two common tangents is how I understand for intersecting circles. Now when I have touching circles, let's see how many common tangents can be drawn for touching circles. As I see for two cases of one being touching externally and the other being touching internally. So in this case, I have tangent 1 and only one tangent which can be drawn for these two. And also I have these. Therefore, as we see the two circles touching externally, I have totally 1, 2 and 3. So there are 3 tangents, common tangents, when the two circles touch externally. But in case of touching internally, there is only one common tangent which I have for the two circles touching internally. Now when the two circles are disjoint, let's see how many common tangents I can draw through this disjoint circles. I have 1, I have 2, I have 3, I have 4. So therefore, the totally T1, T2, T3, T4. So that is, there are 4 common tangents which I can draw for disjoint circles. Therefore, I understand that for case 1, where the two circles are intersecting, I have 2 common tangents which are these 2. For two circles touching externally, I have 3 common tangents which I have here, T1, T2, T3. For two circles touching internally, I have 1 common tangent which is this. For two circles which are disjoint, I have 4 common tangents, 1, 2, cross 3, cross 4. is how we understand the relative positions of circles connected with number of tangents. Now let's see the mathematical property for condition for disjoint circles. So that is, if the two circles are disjoint, then how do we identify for the disjointness through the mathematical equation or the formula? Suppose I have two circles with circle 1 being with center C1 and with the next second circle being with center C2. Then if the radius of this circle is R1 and the radius of this circle is R2, then I have the distance between C1 and C2. For the two circles to be disjoint, the condition is that the distance between C1 and C2 is always greater than sum of the radius. Is how we understand the condition for two circles to be disjoint. The distance between their centers is always greater than the sum of their radii, where R1 is the radius of this circle and R2 is the radius of this circle. Condition for disjointness of two circles is this greater than this.